Hi, good afternoon. My name is Andrea Whitesell. I am the Senior Program Manager for CIRI, and I'm going to introduce Dr. Bloom. I'm going to read a little bit of his bio, and we'll get started. So Dr. Bloom is going to be speaking today about resilience in automotive intrusion detection systems, and just a little bit about him. Dr. Gedare Bloom is Assistant Professor in the Department of Electrical Engineering and Computer Science at Howard University, where he directs the Embedded System Security Lab. His research experience in computer system security with particular focus on real-time embedded systems that have measurable lifetime in decades, right? His current research projects include fail operational methodologies for automotive intrusion detection systems and systematic approaches for building trustworthy distributed control systems with predictable real-time behavior. Dr. Bloom is working on integrative efforts to combine research and education in the subdiscipline of critical infrastructure resilience with us, with CIRI, and he has also generously given us a few summer interns this summer. So anyway, let's welcome Dr. Bloom.
All right, thank you for that kind introduction, and all of those words were correct. And today I'm going to talk about a project that's been going on for about 2 years now, and it is the first leg of that research discussion, which is understanding how to design and roll out automotive intrusion detection systems that have fail operational behavior, and maybe at some point in this talk we'll try to convey an understanding of what that means. If you haven't lived in safety critical communities for a while, then it might be a little foreign to you. But first I want to step back and talk about what kinds of research challenges really get me excited. I get excited about challenges to embedded systems. What are embedded systems? Well, anyone know what an embedded system is out there in the crowd? Only one of you does? Am I going to ask for a def? No, I won't ask for a def. I'll give you a freebie. I'll give you a freebie. So, embedded system is a computer that's put inside of something else. So it's embedded in something. So it's a system, inputs, outputs. There's a computer, that's the controller. Embedded systems are everywhere, and now a lot of them are connected to the internet, and we call that the Internet of Things. My favorite example when I'm giving a presentation, especially in the classroom, and I ask about embedded systems, I usually point to the projector. So that's an embedded system right there. There's a computer in there. Maybe that one has 2 computers. It's certainly communicating. So what is it about embedded systems that are challenging? Well, security is increasingly challenging in embedded systems because we're hooking them up to networks and we're exposing them to remote external access, which allows remote external attacks. If we've learned one thing over time about computer systems, it's that if you hook it up to a network, someone will eventually compromise it. Speed, because I wanted to go with S's. Speed in embedded systems often means latency, actually, more so than throughput. Usually when we talk about speed in computing systems, we usually think about throughput, right? How many cycles per second, gigahertz, can you compute something? How many bytes per second can you transmit? In embedded systems, we might talk about latency, so how many microseconds does it take for you to respond to a stimulus? That's more or less what a real-time embedded system is measured in. And speed is made complicated by the constraints of embedded systems in terms of their computational power is limited. The microcontrollers in embedded systems usually range from several kilohertz to hundreds of kilohertz, very rarely in the hundreds of megahertz range, almost never in the gigahertz range of processing power. And storage capacity is similarly constrained on the order of kilobytes to a few megabytes, usually, of RAM storage. So these kinds of constraints impose practical reality checks for system designers about what can you actually accomplish in an embedded system, and about what kind of security mechanisms can you use that honor those constraints. And finally, safety. Safety in embedded systems is really important, especially when those embedded systems are controlling a physical object that you as a human may interact with. This talk is going to be talking about cars. A car is a complex system consisting of tens to hundreds of embedded systems, and if a certain few of them can go wrong, then the safety of the driver, passengers, pedestrians, other cars can be compromised, and people can get injured or worse. So the research that I tackle in these three areas kind of covers three broad perspectives. One is about real-time cyber-physical systems. So how do we adhere to the real-time constraints, the latency requirements of complex, interconnected, distributed control systems, while doing so in a way that's secure and safe. I'm also looking at the Internet of Things because it's a natural extension of embedded systems. Internet of Things is essentially embedded systems connected to the cloud. And then automotive security, which is the topic of today. And automotive security is generally a nice fit in terms of a car is a microcosm of a complex distributed system that operates more or less on its own. And it makes it an interesting place to study a lot of security challenges and also safety challenges in a real-time way. So we'll talk about why automotive security matters, and I'll talk about some of the defense mechanisms that exist today and a little bit of the research directions that I've been pushing on in automotive security. So let's start with something that maybe we can all hopefully agree on, which is that reliability of systems over time tends to increase as something is sort of used in its natural element up to a certain point. And hopefully at some point in your life you may have seen a version of this bathtub curve. At the start of the bathtub curve, we have what's called the infant mortality, which is the phenomenon that manufactured systems in general fail at a higher rate early on than later in life. So semiconductor chips have this property. Most manufactured products have this property that if you stress test them right away when they're first created, and they don't break, then they're not likely to break until much, much later in their life. And so if you get past this early mortality rate, then the failure rate of manufactured products is sort of at a relatively stable trough for usually a long period of time. And then as aging effects wear down the physical properties of materials, the decay of those physical properties tends to then introduce failures in the sort of wear out stage of life. And so we have this nice sort of property that if we test our systems and we get them through the early infant mortality rate, we can deploy them and we rely on them for quite a long time, and we have a good understanding about where the wear out stage is for tested components. We have sheets of paper you can look up based on mostly military testing of a lot of the parts that are manufactured parts that tell you, okay, this particular screw, just as an example, will last for 30 years in this environment under these temperature, these stress settings. And so you can construct these systems and compose these systems and have some notion of reliability. And once the system is in place, reliability is stable and life is okay. That's fine, reliability increases, but unfortunately, as systems are deployed, their security gets worse over time. If you put a system out there and you leave it alone, its security decreases over time. So this example is a picture of a really old computer that's used in actually a mechanics shop. It's been in use for, I think, 30 years or something like that. And you know that it works for what they're doing. I can just about guarantee you that it's never had a security update. I hope they haven't plugged it into any networks recently. So what is it about security, right? So how many of you heard about the Heartbleed virus? You heard about Heartbleed? So it was a vulnerability, and it existed from 2012 to 2014. So all the computer systems that were vulnerable to the Heartbleed bug were exposed to potential attack from the time that the bug was introduced in 2012 until the time that it was discovered and fixed in 2014. So over that 2-year period, we don't really know necessarily what was compromised as a result. Well, okay. Well, crack was interesting because crack was a problem with wireless networks. And wireless networks were potentially compromisable from the protocol development stage from 2006 to 2016. So that represents 10 years of time that systems that haven't been updated that use the wireless protocols might be potentially compromisable from crack. And then shell shock, which is a bash shell exploit, is related to a series of bugs that have existed in the bash shell since about 1989. So you see there's these huge periods of time over which attackers may exploit a system because of these vulnerabilities that exist that we don't even know about. And that's really the fundamental difference between security and reliability. So vulnerabilities, sort of our understanding of vulnerabilities start when someone says, hey, there's a vulnerability, right? So here's an example of a vulnerability that was alerted in June 4th of, I believe it was 2010. 3 days later, Adobe said they're going to release an update to fix this vulnerability. 3 days later, there's a public exploit available, but there's still no fix. And then 4 days later, Symantec, who does security research, said, well, actually, this vulnerability has existed for quite some time. We think that there are attacks as far back as 2008. So we have seen this vulnerability exploited. We just didn't know that it was this vulnerability. So that red gap there, that's the attacker's advantage. That they're in your system, they're able to attack you, and you don't even know about it. And then, okay, finally, a couple of weeks later, Adobe actually fixes the problem. And then, you know, I should really draw out a line with a dashed arrow that goes on to infinity for windows that actually get rolled out to your system. You know, I actually probably have laptops that are using Adobe Reader that are older than 2010. I don't use that laptop that much, but I should be careful what I open with that. So security is fundamentally different from reliability. I hope that most of us can generally agree on that. And these are some of the reasons why that is. When we do reliability analysis, we're looking at sort of the tolerance of parts or of systems to faults, which are mostly randomized faults or stress-induced faults, or they follow a very particular pattern of usage. As opposed to cyber attacks, which are not random. They are specially crafted, they're customized, they're intelligently composed to try to compromise your system in particular. We don't see security working, and we don't have good ways to measure security. We don't know how to say you are 99% secure or that your security shelf life is 3 years, right? There's no such thing. I don't think there's ever going to be any such thing. And we'll talk about why that is in a few minutes. Another big issue with security is that we don't know how to compose secure systems in a good way. So we can solve security maybe for one piece, and we can solve security for another piece. You put them together, there's an interface between these two secure pieces. That interface is now the weak link that attackers go after. And we don't really know how to solve the composition of secure systems in any sort of foundational way. And going back to this difficulty of measuring it, security is typically thought of as a binary property. Either you have it or you don't. I am secure, or all bets are off. And this kind of thinking pervades information technology, security thought for decades. And I think, we're talking now to the resilience crowd, I think moving beyond that binary property is important from a resilience perspective. And we'll come back to that later. Why is security hard to guarantee? Let's take a brief aside, a step back in history. How many of you know what DRAM is? How many of you have ever used DRAM before? Okay, you have, I guarantee it. Half of you are using it right now. DRAM, dynamic random access memory, is the basic memory chip that's inside of essentially every computer out there that consumers use. Your laptop uses DRAM as its main memory. You probably have about 8 gigabytes of it if you have a modern laptop. So the way DRAM works, I'm going to try to give you an intuition if you don't know how it works. If you know how it works, that's great. Hopefully this sounds right. And if I say anything wrong, just ignore it. We'll get back to it later. So the way that DRAM works is that it's essentially a large array, two-dimensional vector rows and columns. It's an array of these capacitors. A capacitor, if you don't know, is basically like a tiny battery. It stores a charge. And each capacitor is hooked up to a transistor, and you don't have to really know what that is for this purpose. What the transistor does is it either releases the capacitor's charge or it doesn't. Okay? So when a transistor releases the capacitor's charge, that releases 1 bit, 0 or a 1, of storage. And so RAM is essentially a matrix of all of these bits of stored charges. Okay. So they're arranged in banks. That's not so important for this conversation. What's important is that within a bank, each row of memory is located one right after the other, and a row consists of multiple of these transistors, hence multiple bits of storage, typically some integral multiple of bytes for my computer scientists out there. Okay, so the problem is that the arrangement of charges of cells next to each other in rows is that you can repeatedly store a charge into one row and have that charge leak over into the next row. So what this allows an attacker to do is to push bits from one location that they can write to into another adjacent location. This doesn't sound so terrible at first, but there's actually code that tells you how to do this, shows you how to do this, and you can show how to create a bit error in different rows, and you can actually create the bit errors on either side of the rows by writing two rows on either side of the RAM. This is called a row hammer attack. It's relatively new, maybe 2 years old, something like that. You can actually use row hammer attacks to compromise Android devices. It's plausible. It made a lot of, I would say, a lot of news in the security world. Now, if I had, say, 3 years ago, taught you how DRAM works, which is quite possible for some of you in the audience, if I taught you that was how it was worked, none of us would have predicted that this was possible. I mean, this was totally outside my realm of worldview, is that if you write to rows of memory repeatedly, you can cause rows next to it to change. Much less that you can do it in any kind of controlled fashion to cause the operating system to modify its behavior. So this is kind of where attacks change our model of understanding how a system works. Right? This goes back to the point that you can't say my system has security and I guarantee you it's secure for 3 years. I can't even guarantee you it's secure until tomorrow, because someone could come up with something brilliant like Thor's hammer here, and compromise your system the moment you put it out there. Okay, so let's talk about some more attacks, because I think attacks are kind of fun and everyone likes attacks. We can all get on board with attacks as motivating our research. So here's a set of pictures. On the bottom are some celebrities and some well-known people. On the top are some lesser well-known people. And basically what some researchers showed is that by wearing these funky glasses, the people on the top would be classified as the people on the bottom. So this is an attack on AI algorithms that do facial recognition, and they trick the algorithms to take these particular characteristics that the glasses somehow cause the AI to drive down the wrong paths and identify these people, which is quite impressive. I especially like the one on the left there with the guy looking like the lady there. I should probably find out who that is. She looks familiar. Anyway, I guess that's the point, right? So, I mean, you know, we have to understand what are these vulnerabilities, what kind of attacks do they open us up to? This is important, especially as we think about autonomous vehicles and AI as being a part of critical infrastructure. So, security is a system property, and we have to somehow make it work from the top level algorithms that process AI to the bottom level bits that are stored in RAM. How do we make everything secure from top to the bottom? And you know, even lay people are starting to understand, you know, the good guys have to be right all the time in this domain. If the bad guy is right one time, that's a problem. Right? So can the attackers get your software? Can they get your hardware? Can they exploit your system policies, your configurations? Are they bad? Can they surprise you? And this general hypothesis is, you know, I hope that I'm not going out on too far of a limb here. I mean, we have no good way to ensure security at all times for all cases into the future. It's just not worth it. Why? I'm done. No. We have to try. That's why we're here, fighting the good fight. Why is it so hard? Well, you know, we've talked about a number of the reasons. A big part of the reason is that humans are involved as well as critical elements of this. There's this guy, he's rather famous in the flight community, aircraft piloting and such. And the complexity of devices becomes more complex and more dangerous when humans use them, is essentially what this amounts to, is that the digitization of the analog world makes small errors go away, makes noise go away, and that fundamentally is one of the first places that attackers get an advantage. Digital devices tune out the noise, and then the devices create opportunities for human misuse. All right, I think I've beaten that horse enough, but let's see what happens when our assumptions about a system goes wrong. So this is a Volvo or Volkswagen. It has automatic braking capability. It's part of their the automated driver assistance feature. And so we're going to have a live demo recorded of this. And it didn't work. It just didn't work. Human belief that their system is correct causes problems. This is even in the absence of security problems, right? We can't even get systems right without attackers. I don't know how much hope there is. We have to keep working really hard on these problems. The first known fatality involving an autonomous vehicle and a pedestrian happened earlier this year. This happened in California, I believe. It was a self-driving Uber. It was actually, I think, the same kind of car we just saw. In fact, Uber turned off the automatic braking system for their self-driving car because they say that it interacts in bad ways with their automation software. Wasn't that convenient? So interestingly, so this vehicle was moving within the speed limit. It was going 43 miles per hour. It identified an unidentified object 6 seconds before the crash. And 1.3 seconds before the crash, it made the emergency alert for the driver. But the driver did not apply the brake until a second after the crash. So this is a breakdown primarily in the changeover between the automatic driving system and the human operator. It goes to the point that automation is not quite ready to hit the streets, if you pardon my expression. Let's go back to that thought about using glasses to fake out facial recognition. How about using strips of tape to fake out your vehicle's computer vision? So here's a couple pictures of stop signs that have been carefully modified with black and white tape, and now the computer vision algorithms think that the stop signs are actually speed limit signs. You can imagine what the ramifications of this are. In the real world, we often make assumptions that break down. They break down because people do strange things. Maybe they stick stickers where they don't belong. Maybe they shoot holes in signs that they shouldn't. Maybe they just take signs out of the roadway and put them other places. Humans tend to be able to work through these kinds of problems as drivers, but computers have a hard time. This would be, I guess, a physical attack on a cyber system. So where are we going with this? Well, IoT. Yay, the Internet of Things. It's going to make everyone's life better, right? We're going to put computer chips in everything. We're going to connect them all to the cloud. You're going to be able to monitor your heart rate and your sleeping patterns with your watch at all times and be able to know where your car is and where your keys are. And you're going to be able to find parking whenever you want to. And you're going to be able to order dinner on the way home and have it there for you by the time you get there, right? And oh, by the way, the restaurant's going to know exactly where you are too. But that's okay. Share all data. We can make everything possible. We just need enough data, and we can machine learn on it and do whatever we want, right? And if anything is not connected, that's a problem, right? That's a problem. We need connectivity. We got to have it. It must be connected. Okay. Again, connect a computer to a network, and you leave it there. Eventually, it's going to get compromised. That's just the way it is. We have to be very careful about how we treat our computer systems, especially when they're responsible for taking care of us. So now I'm going to show a bit of a segue here. I said everything is gloom and doom. Well, maybe not. Maybe it's actually not possible to hack into vehicles and cause them to crash, right? I mean, Scientific American is a pretty upstanding journal, if you ask me, well, magazine. I know I learned a lot from it when I was like 12. Okay, so in October of 2015, this guy wrote about car hacking is nearly impossible. Now, okay, a couple months later in Fortune magazine, car hacking is easy. Which one do you think is true? I like where your head's at. How easy is it? You can go online and buy these little devices. The one on the left is, anyone know what that is? It's a key fob. Doesn't look like any key fob you ever used. It'll spoof and capture and replicate and allow you to essentially open and close doors, or if someone has installed a remote starter, woo! Free cars, I like it. Would anyone actually have motivation to steal a car? If for no other reason than to take a joyride or, just anger someone. You know where this really gets interesting, though? is in supply chain management, trucking, logistics, transit, haul, freight. Huge motivation. Something fell off the back of a truck, right? Okay, on the right, I just about guarantee you don't know what that is. You might recognize one or two pieces of it. Up there on the top, that's actually the onboard diagnostics port connector, OBD2 port connector. Onboard diagnostics is how car mechanics find out what the little lights on your car say. They just plug a little device into a little port that sits somewhere just underneath your driver's steering wheel, usually right above the accelerator. There's a little panel there. They can plug it in. By the way, you can buy a little device and plug it in there and read out what the codes are too if you want to save $100. I don't recommend doing it, but you can. So this device plugs into the OBD2 port, and then it installs, and it has some sort of malware in it. But the malware doesn't target the car. The malware targets the diagnostic tool. The malware infects the diagnostic tool and then infects other cars. So it is a malware propagation tool that can infect diagnostic tools. That's kind of clever, if you ask me. I wish I had thought of that. Not for malicious purposes. I mean, it's just cool stuff. In fact, right now, Black Hat's going on, and I almost guarantee you there's at least one talk about how to hack automobiles going on over there. Pretty reliable source. Why is it so easy to compromise cars? Because they contain tons of software. How much software? More software than just about any other system that you could point me at. A single car contains upwards of 100 million lines of code. This is incredible. A lot of this code is redundant. A lot of it is spread over multiple computers within the car. High-end luxury vehicles have about 100 computers inside of them. Computers to control the windows, the doors, the satellite phone, the satellite TV, the satellite itself, the GPS, the rear view backup mirrors, the side panel mirrors, the detectors for the automated driving, so forth. Every single feature, slap another computer chip in there. Software, 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 lots and lots of software. Why so much software? Well, because software is lighter than hardware. That's the only reason. We cut out a whole bunch of hardware from vehicles in order to save on the cost of the vehicle. We replaced mechanical parts with electronic parts. We replaced mechanical pipes and shafts and gears with wires that communicate the angles to rotate things rather than actually rotating them. Saved on weight, saved on cost. Good deal. A couple pennies for a chip, a couple pennies for a processor, versus a couple dollars for steel piping. Well, not steel, but you know what I mean. So that's why. What about all that software? Well, if I've learned one thing in any of my computer security classes, it's that the more complex software there is, the more opportunity there is for attacks. Software complexity makes lots of opportunities for cyber attacks. Now, most of the software is actually not accessible to remote attackers, but some of it is. And the parts that are accessible from outside of the car or from someone remotely are the more likely to be compromised parts because they're the more complex software for the feature-rich luxury features that you want, like your Bluetooth connection to listen to your music in your car. If your phone can communicate with your car, someone else can communicate with your car. That's the moral of my story. Disabled the Bluetooth connection on my car. Maybe I'm a little paranoid, but you know. When I find out that a president of the United States is willing to use a vehicle with these features, then I will consider using a vehicle with these features. This is, okay, a little bit of a nod to Dick Cheney's disabling supposed, pretty well established, disabling of the wireless connectivity of his pacemaker. Okay, so lots and lots of different functionality. Each of these different kind of sub-pieces of a car is connected or controlled by what's called an electronic control unit, ECU, electronic control unit, which is really just a fancy way of saying computer. It's an embedded system. It usually controls one aspect of the car's functionality. So airbags are controlled by an ECU, an electronic control unit says deploy the airbag when it receives a signal that says the car is in a collision. Well, how does it know it's in a collision? Well, there's another electronic control unit somewhere with a sensor that detects compression of the vehicle and also detects a sudden change in acceleration that is more than the vehicle itself naturally can cause. So when the non-safety critical code that's in, for example, your infotainment center, your satellite radio, what have you, when that is compromised, so what? Maybe someone can get in your satellite radio, muck about, I don't know. The issue is that your satellite radio is connected to your engine. Why is your satellite radio connected to your engine? I don't know. It just is, because of cost and historical reasons mainly. Okay, the attacker has opportunities because there's tons of computers in your system. All they need to do is compromise one of them in order to get access to the rest of them. Now we're starting to connect our vehicles to the internet. There's propositions for vehicle to vehicle and vehicle to infrastructure connectivity so that your car can, for example, communicate with traffic signs and know they're about to change and, slow down accordingly. Well, that's all well and good until a malicious traffic signal messes with your car. Okay. And complexity keeps on increasing. You can download software for your own self-driving car. I haven't actually tried it. Played around with it. But, if you're so inclined, you can download an entire self-driving car software stack from NVIDIA. Yeah, because when I think safety critical systems, I think NVIDIA. We might have to edit that part out. Okay. So what's going on here is that although different electronic control units are connected to different networks within a car, different computer networks, all the computer networks are connected to each other. They're connected to each other through gateways, through gateway routers, basically, if you like. So your infotainment cluster, depicted up here, is connected to an infotainment bus, which is itself then connected to a network that's connecting all of the different vehicle networks. One of the reasons for this ubiquitous network connectivity is for diagnostics. So you take your car to the shop, and they can plug into the OBD2 port something to tell you what's going wrong. And that port can connect and talk and control everything within the vehicle. Oh, by the way, you can install aftermarket plugs in the OBD2 port. I talked about this before. Have your phone talking to your OBD2 port. I think Verizon sells a little thing that you can just buy off the shelf now. Plug it on your OBD2, because more data is better, right? And I have full confidence that an attacker would never get in through your car that way. I don't. Do not do that. Don't plug anything into your OBD2 port. Okay. There's also some legal issues about that, but yeah. Okay. So an attacker can exploit something in the infotainment cluster, which is the way that most of the demonstrated cyber attacks on automobiles have been shown in the past. If you've ever seen any of the videos, I really ought to get one of those. Basically, they compromise something like the Wi-Fi or Bluetooth connection. They compromise a control unit attached to the Wi-Fi or the Bluetooth connection in the car. And then once they've got access to that, they can access anything on the infotainment bus, and they can attack the gateway router, which is what they do. Once they compromise the gateway router, they can control the car. They can issue commands to the brakes, the steering, the accelerator, whatever they want, and keep you, as the driver, from sending any commands yourself, so you have no control of the vehicle. So this is the sort of the example of attacks that have been demonstrated. If you've heard about them on the Jeep Cherokee, by the guys at DEF CON and Black Hat a few years ago, and then there's been a few others in recent history. So what are we going to do? Well, okay, we're going to architect stronger systems, right? We're just going to solve and patch the problem. Well, then, to some extent, that's true. There's two general approaches to try to deal with this problem. One is to increase the authentication of messages being transmitted on the network so that we no longer accept commands to change the engine RPM when those commands come from the Bluetooth electronic control unit. Because why should the Bluetooth control unit be telling the engine what to do? There are some historical challenges with using message authentication in these networks. These networks, they don't have a lot of capacity for extra bits in order to add, for example, you might think, message authentication codes. Well, there's not necessarily enough space to add a message authentication code within the frame of the messages that are transmitted on this bus. So one area of research that's still open is how do we authenticate electronic control units in a way that is, I would say, compliant with the resource constraints of the network. In this direction, there's been two recent works that have come mostly out of University of Michigan and out of Dearborn, where they use physical properties of the network messages to try to authenticate or fingerprint the electronic control units. So the physical properties that they're looking at are the timing property and really the clock skew of messages from an electronic control unit. So they try to measure what the clock skew of an electronic control unit is in order to say, that's the electronic control unit that's communicating. So then if I fingerprint the wrong electronic control unit saying something, then I can say, no, let's ignore that. And then, of course, because security is a cat and mouse game, someone said, okay, well, I can actually obfuscate and hide my clock skew, and I can make my clock skew look like anyone's, so that doesn't work so well. And then someone else says, okay, well, maybe we'll use power signatures instead. So right now, an interesting question is, can power profiles of messages be used to authenticate or really to fingerprint electronic control units in order to authenticate them? I'm not doing too much work in that area. I think it's a nice area, but it's complementary to the work I'm doing, which is, okay, suppose you have perhaps identified a way to figure out there is an intrusion, or suppose you have these features like physical fingerprints that you think are useful for authentication. Perhaps they're also useful to detect intrusions. Useful to detect the fact that someone is trying to spoof messages. What then? What do you do? I'll pose this question. What do you do when you detect a compromise? Okay, what do we do in a server or a desktop setting? Well, we pull the plug. Right? That's what we do, and we put that thing into a safe harness, and then we analyze it, and we see if we can figure out what the attacker's done. We try to clean it to some extent and try to mitigate the harm. Right? Can't exactly do that with a car when it's going 60 miles per hour down the interstate. Right? What do you do? So that's one question we're looking at, is how do we respond to attacks in a way that ensures the safety of the vehicle? And then, what are we going to do in order to get back to an operational state somehow? So the notion that I'm sort of working toward is this idea of having intrusion detection systems that guarantee some kind of fail operational semantics for a vehicle. Fail operational is a concept from the safety critical community, which means that a system, when it fails, continues to operate. This is in contrast to the typical model that's used in computing, which is fail-safe, or fail-crash, if you like, where a system fails into a safe state or fails into a non-operational state. The difference between fail-safe and fail-operational, I think a great distinction is an airplane. When an airplane's engine goes out, you can still kind of control the airplane and try to coast it down to the ground. So that when you're taking off over the Hudson Bay and you fly through a flock of birds, you can still attempt to land it. So the vehicle still has some operational capability, but it's greatly reduced. Okay. Fail operational is a mindset. It's a mindset. So the idea here is that we're investigating methods for intrusion detection and response that allow an automotive network to have fail operational capability, meaning that when an attacker penetrates the system and they reach the gateway, we detect this behavior and we don't allow that transitive attack to the safety critical functionality to happen. We degrade the performance of the infotainment bus. Maybe we disable that bus because it's not critical to the behavior of the safety of the vehicle. And then we can restart electronic control units on that. That's one method to try to recover. We can simply disable entirely that feature, and the driver gets upset because, hey, my Bluetooth stopped working, but at least they're not dead. So some of the results that we've come out with, we've really started to identify some new features for intrusion detection, for anomaly detection in vehicles. We've been collecting data from cars through partnerships. We're trying to understand what are the fail operational modes, where can we draw the line between what you can sort of stop and degrade versus what functionality should be continuing to operate. Vehicles themselves have a fail mode, as it were, and we're looking at how does that fail mode interact with cybersecurity. So as an example, one attack that's particularly hard to deal with is a denial of service attack on this bus, where you just flood the bus with a message or a couple of messages. It could even be an authentic message, and no other message can get through, which means you can't drive the vehicle. The electronic control units will detect this as an error of the bus, and they'll enter a sort of a kind of a shutdown mode, but the vehicle still rolls at a certain low speed. I guess, I don't know why, but I guess it's enough that you could bail out, but the vehicle doesn't stall. I don't know. So understanding why or what fail modes exist in these systems and whether they're sufficient for security or not is part of what we're investigating as well. So we've looked at using data provenance in vehicular systems as one new feature for understanding, trying to get at root cause analysis for failures that stem from cyber attacks. And trying to better leverage, like I talked about, some of those alternative physical fingerprint approaches that have been laid out, and how do we integrate physical information with cyber information and really try to come together with a cyber-physical solution that understands what's going on within the software, understands what the software and hardware are doing, and understands the mechanics of the system as well. The provenance-based approach that we've been looking at tries to understand how do we collect provenance. Provenance, by the way, is really a kind of metadata which tells you where data came from. It's useful in forensics to track data back to the source of decisions, to the source of data. Maybe two of the key challenges for provenance are storing provenance, because metadata can greatly exceed the size of data itself, and trying to manage that is a challenge, especially in a resource-constrained environment. And then from a timeliness perspective, actually collecting and analyzing this metadata in a way that allows you to respond to attacks while they're happening is still an open area for investigation. So the approach that we've been taking is to instrument electronic control units and to instrument network controllers in network vehicle networks with trace-based provenance, which basically means we generate logs of events that the automotive system generates, as it were, and then convert those into a provenance format that is amenable to anomaly detection. So this is open work. We've had a couple of early results came out over this past year. The student who's working on that is now moving on, and I'm hoping to keep pushing this on down the road a little further. We're also trying to understand how do we measure trust in machine learning. I talked earlier about sort of adversarial AI and about sort of fooling artificial intelligence and machine learning. We want to know how do we increase or measure trust for sensor-based data, which is by and large what gets input to machine learning algorithms in these kinds of systems. And in the Internet of Things, much of the data and much of the hype of Internet of Things is about sensor data, data that's been sensed about the real world. That's what it's all about. So this is work that I've started underneath the DHS support that we're looking at, and also with some seedling funding from Northrop Grumman, who's been a great proponent of these kinds of trustworthy data science algorithms. And some bad animation. We've looked at trying to understand what are the right kinds of intrusion detection systems for automotive vehicle networks. There's lots and lots of them out there now, and we're making headway in understanding which ones to use. It seems that the message frequency detection, anomaly detection algorithms appear to be particularly well suited for the kinds of attacks that have been demonstrated. The general attack that sort of takes over an electronic control unit and then takes over or spoofs the behavior of safety critical driving features has this kind of behavior that's been described by one of our partners as whack-a-mole. Essentially what the spoof attack tries to do is once an authentic message is sent, the spoofer tries to send their injected message immediately or shortly after the authentic one. Because all of the other electronic control units on the network will interpret the spoofed one as what they should do for the duration until the next message arrives. So the idea is you allow the authentic messages to continue, the attacker allows the authentic messages to happen, but they override them so quickly that the effect of authentic messages is essentially lost. And so the attacker's goal is to try to whack that mole as quickly as it can. Usually in the literature, what we've seen is people say we inject the messages at 10 times or 20 times or 100 times the frequency of the authentic message. That is enough, that is what I should say, enough to get the attack to be successful, but it is not what an attacker has to do, right? So it is sufficient that an attacker can inject at 10 times the rate, but really all that's necessary is the attacker has to inject at the same frequency of the authentic message just immediately after it, sort of piggybacking. This kind of knowledge is something that we've discovered through our investigation. It hasn't really been very well articulated in the research community around this space because a lot of the attacks have been done sort of in this kind of, I'll say, glorious way of we compromised this vehicle and we gave the talk at DEF CON, right? So there's not as much detail, and to a great extent, a lot of times, it's hard to elicit good, rigorous research bounds around cyber attacks and vehicle security. Let's skip that. So we have some intrusion detection system prototypes that we're using some log data from a Toyota Prius, some simulated attack logs, and we have some controller area network logs from some real vehicles in both normal driving modes and attack modes, but the actual vehicles are not We're not allowed to talk about what they are as part of the arrangement for having these vehicles. So this has been one of the interesting and more challenging aspects of vehicular security. I went into this kind of naively thinking, okay, we have access to these vehicles, we can do some research with them, and we can publish some good results. Well, it turns out, okay, well, you can do the research, but you can't say what the vehicles are. Oh, you can't publish those logs. Oh, your research is essentially not reproducible anymore, and it becomes harder to say, look, we did a good thing. So this has been a sort of a challenge, but we're getting closer to coming to some sort of arrangements that other people say are legally okay, which is we're going to anonymize, well, not us, someone else, is going to anonymize these logs so that you can't figure out what the vehicles are, they claim. So that's coming along, and so hopefully we'll be able to share results a little bit more completely. So this is collaboration with Oak Ridge National Laboratory, Iowa State University, and Howard University, an NSF project. And perfect security is impossible. We must have resiliency. We have to admit compromises happen, and we have to figure out how do we work past them. And this is my lab as of, well, the end of this last semester. In fact, Ebel did much of the work on Provenance, and he graduated, and we've got 2 or 3 new faces that get to come up on this wall in the fall. So thank you, and I think we already have a question.
Out of curiosity, is pardon me. So out of curiosity, this you not being able to discuss these vehicles you're using, is that because they were a gift or, okay, all right. So it's not that there's some like sort of terms of service about the vehicle itself that prohibits.
I think if you bought one
research.
of these, you might be able to talk about them, but you would definitely want to run it past your general counsel first.
All right.
because these vehicle manufacturers, I mean, they got these huge legal teams, and they really don't want to see their names associated with even research attacks on their vehicles.
So you mentioned a couple of things, that you have this computerization, millions of lines of codes, and that you're replacing hardware with software. And I took that to mean that physical linkages and that kind of thing are going away.
Yep.
And basically,
have gone away.
When you turn the wheel, something signals to something, and there's no actual.
That's exactly
mechanical
correct.
linkage. Now, you also mentioned the Hudson. So I'm guessing, and maybe I'm a little out of my expertise here, but that with avionics, at least with that airplane, it was in some intermediate stage where it had onboard advanced avionics, but it still had the mechanical linkages.
I believe that's
when the linkages
correct.
go away, how can you
Right.
guarantee operational? What was the term you used?
That's right, fail operational. And for vehicular systems, it's not clear that you can. I mean, if the safety critical network goes down, then it's not clear that you could guarantee that. We're looking at the broader network level, if we can isolate the safety critical paths from the infotainment and the other paths, then the network as a whole is fail operational, subject to these assumptions, right? That the attackers come in through the remotely accessible pathways, if that makes sense. But you're absolutely correct that avionics and for example, space shuttles as well, they have these backup modes that ultimately fall back on mechanical linkages, which no longer exist in cars. Scary, I know. Makes me want to go out and buy an antique.
I'd say vintage is going to be more than anything.
That's right, that's right.
That's what I was thinking, if they would go back to the way cars was built, so you still have your mechanical system. I would think that if you shut it down, just keep where the old cars was built, and that would probably help solve.
Yeah, the problem is no one wants to pay for those. And it's more expensive, it just is. Or so they say, you know.
I think I understand now. If we had perfect message authentication for vehicle components, would this be a solved problem?
This particular style of attack, I think, would be greatly mitigated by message authentication.
I'm wondering, based on the way that, based on the attack phases of a vehicle, you have to target one of the sort of network connected, modems that exist somewhere in the system. How many legitimate flows within a system can be exploited by an attacker, right? So like if we had like a control flow integrity type solution in a vehicle, would that solve the problem, or would there still be a lot of issues?
Right. The problem is the problem, and actually really even piggybacking to your first question, the issue is that even authenticated ECUs that are compromised can still try to compromise other ECUs using their authentic messages, right? It's like traditional sort of thinking about traditional cyber attack, right? You can send an authentic message, but it has a payload that's malicious, right? It's the same thing here where if I get into the Wi-Fi electronic control unit, I can try to send authentic messages into the gateway that attempt to compromise the gateway, right? So I think to that extent, you still need some kind of detection of that kind of behavior. And it's not clear to me, I don't know the answer to your second question in that capacity, whether the valid information flows are sort of enumerable, I think is more or less what you were asking about. I suspect that there are enough limited ones that it's possible to construct a model of the data payloads and message IDs that are sort of valid. But actually doing that from an external perspective is probably hard. If you had all knowledge of the automotive integrated automobile, you might be able to do it. So auto manufacturers might have that capability, but it's not clear that they would have that because they're still just integrating parts from other vendors.
I guess another way, sorry, Sibin, another way of phrasing it would be like, so that clearly the safety critical system is networked for a reason. Like there must be something going on that the safety critical system needs to be connected to everything else. So, if we could authenticate devices so that they couldn't forward messages, if we had a really naive whitelist to sort of confirm that only legitimate components that were supposed to communicate with the safety critical infrastructure were allowed to, how big would the problem be then? Because
yeah, so I think then the problem distills down exactly to securing just the gateway to the safety critical network. And that is a direction that some of the emerging automotive standards are going, is back to trying to dissect, not really dissect, split the networks physically more from each other. The big reason that all the networks are connected is the diagnostics.
You just killed Tesla's business model. They're like a giant iPhone, if you consider. Like you can do all kinds of functions and connect all kinds of things to it, right? But the problem is people are just throwing features into cars that they think we need and we think we need, but we're not sure. But talking about authentication, like a lot of this happens because CAN has really no authentication, and it sends a lot of messages in clear text and stuff. There are protocols like CAN 2.0 and FlexRay and others that people are starting to use, which have some of these features. Like how much do you think that mitigates many of the problems that you mentioned?
Okay, so first of all, CAN isn't really going away, for better or worse. And FlexRay actually, it seems like it might be on its dying legs itself. But there are emerging protocols that do have more capacity to handle authentication and even encryption. It's not clear without seeing how systems are architected with those kinds of networks, how much of this problem remains. I mean, it's sort of, it's hard to answer that question without really having an automotive system or an automotive architecture that sort of uses that kind of through and through. But it also goes back to what Adam was saying about sort of, if you have perfect authentication, what's left, right? And what's left is still the room that an attacker has to work within as an insider and to submit authentic messages but malicious payloads, or to try to compromise essentially multiple electronic control units and coordinate attacks to some extent. And one of the attacks that's really hard to actually solve in any of these systems is denial of service, even with authentication. Is kind of difficult.
So you mentioned the limitations, computational limitations of the ECUs, but it seems you don't have to have, it seems that if you have, for example, strong security on, I believe it was the backbone in your diagram, that you might.
The diagram is simplistic. There's not really a backbone, but yes, there is some centralized node of sorts that does coordinate some of these.
That's where you can have your multi-gigahertz processor and do what you need to do, and maybe run VPN, SDN, whatever.
Potentially, yeah. If you
there.
can convince the car manufacturers to do that, then yes. And I mean that's sort of where we're envisioning our solution being deployed. But again, it's sort of there's a huge sort of cost-benefit analysis that ultimately someone is going to have to do to determine whether or what security functions are actually worth implementing. I'm reminded of Fight Club, and if you're familiar with Fight Club, there's a rather kind of questionable scene about A plus B is less than C, then we don't do a recall. Well, it's going to be the same kind of math at some point for automotive manufacturers. If the risk of a compromise is less than the cost of rehabilitating it afterwards, then they're not going to worry about the security, or they are. I mean, that's a business case for resiliency, I suppose, but that's not my area. Maybe someone at CIRI is interested in studying that. Okay. Yes?
So, Doctor, when you mean that hacking cars are easy, like, do you mean remote hackings or like on-site hackings? Because
Okay, so physical hacking, on-site hacking of a car is essentially trivial. It always has been, to some extent. I mean,
or there.
they were local devices. They were near communication, or they were physical plug-in devices.
They boil down to common theft, so they've always been there.
That's right.
So
Those
how
do.
difficult is like remote hacking?
So remote hacking is still difficult because most cars don't have widely accessible interfaces. But as the connectivity of cars increases and we start to see communication between vehicles and each other, and vehicles and infrastructure components and roadside units, then remote hacking becomes as easy as physical hacking, or easier. So that's
I recall hearing a case some years back where I believe it was GM OnStar, and somebody reported a car stolen, and GM was basically able to slow the car down to 5 miles an hour, and then, or some very low speed, and then the car was stopped.
That's right. The OnStar has a capability to disable a vehicle remotely. And I mean, there's always been sort of low jack or whatever as well. And then the question becomes, okay, can someone remotely access that? And the answer is, yeah, probably. All they have to do is be able to compromise the OnStar protocol, which, well, it's remotely connectable. I believe it's compromisable. Generally speaking, though, spoofing satellite signals tends to be harder than Wi-Fi signals, generally speaking. You also get in more trouble for doing it if you're caught. Anyway. Okay. Thank you.